Okay, so our second speaker in the afternoon is Bezrukavnikov from MIT, who will tell us about Langlands duality for the affine Hecke category.
Thanks. Thank you very much, and was very grateful to the organizers for the honor and the pleasure to give this talk. Very much impressed by everything I see. Okay, so this is the down. Okay, so let me start with a little bit of history, and so there's Langlands duality in the title, and this theory goes back to a letter that Langlands wrote to Andre Way in January of 1967, and so this was there he initiated this approach where non-abelian reciprocity laws in number theory are expressed in terms of automorphic representations, and more precisely as a link between two sides, where on one side you have automorphic representations of a reductive group, and on the other hand we have data involving Galois group and the so-called Langlands dual groups. The group whose root data is dual to that of G. And in particular, for today's talk, I will focus on local Langlands conjectures, which is just classification of irreducible representations of a p-adic group. Classification is given in terms of their dual group. And I will get there in a few slides, but just to mention the kind of main point is that so here we work with this story talks about representations, and so representation is maybe something like rho V. V is a vector space, but then later in the geometric theory that I will mention in a few slides, V is categorified to a category C, and the phenomena that I find fascinating is that this category C often turns out to have a completely independent interest, so to be something that a representation theorist or perhaps a algebraic geometer can be interested for completely different reasons. And so although very powerful applications of this idea within this theory of automorphic forms, what I will be talking about is a sort of small contribution to the attempt to understand the implications of the reciprocity laws in completely different areas, not number theory, not theory of automorphic forms. Okay, so so let's for now focus on a special case proved in 1987 by Kazhdan with contribution from Victor Gainsbourg. So now let me be a little more precise, and so we fix a local non-Archimedean field, which is a finite extension of QP, or field of Lorentz in one variable. We start with algebraic group and take the group of points over that field. So you can think of the example of matrices, invertible matrices over that field. That has the standard maximal compact, or write it, but O is the p-adic integers, so maximal compact G04, and it has an Iwahori subgroup, which is so it's the group of for JLN, it's a group of matrices in which Y and G04 and whose reduction modular uniformizes alpha triangular. GL2, then I is the group of matrices of this form. Pi is the uniformizer, and star the element in the ring of integers. And then it turns out that this set of representation has the first kind of very rich and interesting piece, namely the principal component in the set or category of representations consists of those representations which are generated by the vectors invariant under that group, under the Ivanhoe group. And the classification of such representations were obtained, as I said, in 1997. Namely, it's the set of these triples. It admits a canonical bijection with the set of the triples as U psi, where S is a semi-simple element in the dual group, U is a unipotent element in the dual group, and these two elements Q commute, as written. And psi is an irreducible representation of the group of components. And to simplify the discussion, I assume that G is simply connected, otherwise formulation is a little bit more involved. And I will not, of course, recall the proof of this, but I want to recall the key ingredient in that story. And the key ingredient is the how do you connect to the dual group? Again, start thinking. It's just completely, it's not there, but it comes in through this very concrete statement that first of all, you reformulate your problem in more concrete terms. You take this algebra of Ivanhoe invariant functions. And that algebra is something very concrete. It's this affine Hecke algebra. So maybe I didn't write it, but here, H, C, O, I is the so-called affine Hecke algebra. And its size is like the size of the Weil group, so there's cosine sign bijection with the Weil group. But the algebra is more complicated, and the key point is that it has this coherent realization. So you go to the dual group and start playing a completely different game. So you take this variety, you take the dual algebra, and then you take this n tilde, which is the cotangent bundle to the flag variety, and it maps to the algebra by so-called Springer map. And then we take the fiber product, so this is Steinberg variety of triples. So this is our main space. The main algebraic variety to consider there. So it's called Steinberg variety. And then we consider the K group of equivariant sheaves there, and this KQ is maybe explained in the next slide. So this is the K group base change to C that way. So representation, K group of representation of GM is just Laurent polynomials, and you send this variable to Q, which is the cardinality of the radius. And so again, this is not the most not the technical core of this argument, but it's the conceptual core of this theorem, because that's where you bring in the dual group, or Kazhdan, Lustig, and Ginsburg brought in the dual group. And well, I want to make this two remarks. So one is that this realization of the algebra comes with a module, because if you have x like times x over y, it's like matrices. So we act on x. So here it's KQ of the fiber product x and KQ one factor. And this factor, this module has a very natural meaning on the original p-adic side, namely it's the space of Whittaker functions of G mod I. I'm not recording the definition, but it's something ubiquitous in representation. Kind of generic, it has to do with taking generic Fourier mode in many other, happens in many other subjects in math. And then the other connection that I want to emphasize and maybe address later. Okay, so I said that this affine Hecke algebra, its size is like something very combinatorial, like a fine Weil group. But as a ring, it's not as simple, but it is still related to something, if not combinatorial, then topological. Namely, it has a quotient of the group algebra, a fine braid group. So maybe I didn't write it, but a fine braid group is a fine Weil group is a quotient of be affine, like just the usual braid group. Let's see a picture on the next slide, but like when you have a braid, then from a braid, you get a permutation of set from 1 to n, because like you have even number of pegs where your threads start, and then the braid defines a permutation if you trace where each thread starts and where it ends. And similarly in the affine case, you get a map to the affine while group, and the Hecke algebra we're interested in, it's a quotient of that. And yes, so I'm saying that this affine while group, so it's actually pi. In general, it's pi 1 of the set of regular semi-simple conjugacy classes in the dual group, but in the for our favorite example of GLN, it's just the fundamental group of configuration space of points on the plane. And as you know, the braid elements in the braid group can be written by a braid diagram. And here it's very similar. You just have to imagine that this diagram is drawn on a cylinder. So artistic abilities are less than impressive, but that's you should again. But here it's a braid with 4 threads, which is run on the cylinder, starting on the top and going. And I kind of, in various points in my life, I contemplated this kind of philosophical question of how this appearance of the braid group, does it really underlie a more substantial connection to topology, geometry of local systems, etc. And well, it's certainly a rhetorical question here, so I will try to illustrate that it does, although maybe more other ways which I still don't see. Okay, anyway, so now I'm addressing the point that was already mentioned, so that the classical Langlands story started in that January 1967, but then later, maybe in the late 80s or early 90s, exact date, and I think it's Denison and Greenfield initiated the geometric Langlands program, which has its roots in Greenfield's work on the classical Langlands story for functional field 2, but then again, this is not the word they used, but using today's terminology, you can just say that a geometric Langlands is just a categorification. Classical Langlands along the lines indicated here. So vector spaces are replaced by categories in a certain way, so that motive and you know the theory. Time to recall the theory, but standard idea, standard step in that story is to, use some specific categorification of H on the side. Namely, you consider logic sheaves on the corresponding stack. So you start with set, and now you realize that this set is a set of points of a certain stack, and then you consider logic sheaves on that stack, and then you can go back to functions by taking trace of Rabinus. So living under the rug, I'll just say that this is certain interesting category of geometric geometric origin, so the constructible sheaves, which is here. So this is the affine Hecke category. And it comes with a module, Whittaker sheaves. And the result that I obtained some time ago is that you realize that this isomorphism of algebra and modules used by Kazhdan and Ginsburg actually underlies an equivalence of categories, like written like that, and there is a little bit of fine print there that we have to think of this Steinbeck varieties derived scheme to make this work, but never mind. And so yes, and so there is an equivalence of monoidal categories. There is an equivalence of modules, which was written earlier. So everything works out. And yes, just to make a little bit of contact with my first slide with Langlands 1967 letter, again, I will not explain the proof but I just want to indicate that the core ingredient of the proof also has a kind of global nature, is also a reflection of this reciprocity laws, which here manifest themselves in a kind of a geometric way, namely, so there is this, so this p-adic group that we, sorry, I mean, maybe I should have said a little bit more about this notation. I kind of, yeah, I ran through it a little bit too fast. So maybe the meaning of this LG here. So LG. Okay, so maybe I'll say now what is it. Yeah. So so what is the loop group? So first of all, in the beginning, I said that G can be, so F can be a p-adic field, but now I want to assume that it here. So F is an extension of F of T. And then the point is that LG is a loop group, so it's we think of it as some sort of algebraic object of a finite field, such that this holds. So this is an infinite dimensional kind of algebraic variety, or more general, over that field. And it contains an algebraic subgroup of GO and Hori, which all thought of as infinite dimensional algebraic group schemes, and so that's what allows us to do this. And then when you the Whittaker, it just means that we can there is this LG mod I is the so-called affine flat variety. And so this is infinite dimensional algebraic variety, so it's kind of ind scheme, so union of finite dimensional ones, kind of int reductive scheme. And yeah, so Whittaker sheaves are just some subcategory in just sheaves here. No. Okay. So any questions about this? Okay, maybe I'll say something more concrete about it later. But yes, so well, the statement is local in the sense that if P of T is a local field, again, you can think of it as functions on a formal punctured disk. So spec of FP of T and something like formal punctured disk. And but the construction actually uses an embedding of this into a actual curve C, and Benson-Greenfield construction, which kind of allows to consider data. So here we have a curve C with a preferred point fixed there, but there is a data involving running points, and then the rest of fusion construction when the points come together, taking by cycles. And so this is the way this global curving comes into play. Okay. And so, yeah, so I want to keep returning to this affine Bray group. And so it is still there. So here it's easy to say that a basic feature of definitions, once you have things set up, it's not hard to see that you get this map from B affine to the invertible objects in this monoidal category. So in particular, it acts on M and on H. So now I want to talk about applications and relations to other chapters of representation theory, as I said. But for that, I want to kind of emphasize that there is a key feature here that not only we get this equivalence of triangulated categories, so not only we get the description of this category of constructible sheaves in terms on this coherent side, but we also get a description of the T structure. And if this term is familiar, it just means that kind of all the categories that appeared so far were these triangulated categories of complexes. But we actually have some abelian category sitting inside. And this is actually, well, it's called abelian part, but it's also like part of this story, in the heart of this story. And so on the constructible side, on the p-adic group side, you have this perverse sheaves. But the point is that these perverse sheaves can be described on the coherent side. At this point, I only mentioned the term in terms of noncommutative Springer resolution. It's something I will say a little more about later, but this is some structure which is characterized in terms of BFI. So to get a little more precise. So since I'm not giving many details, let me just give at least some examples. So I will again. So this, So there's no. What is this non-commutative Springer resolution? So as I say on this slide, it's just some algebra with derived equivalent to n tilde. And so you can also, n tilde actually is the resolution of singularities of the set of important matrices. Okay. For example, maybe G is SL2, and N is this quadratic cone, and n tilde is its resolution by void here. So there's this quadratic cone, and it's I think it's resolved by this starting one. So a quadratic cone that you can think of as A2 minus 1. And so this A is what's called non-commutative resolution. So it's an algebra over this N. So it's centered exactly functions on N, and in algebraic geometry, there's this concept of non-commutative resolution. So it's one of those. It's derived equivalent. So maybe I'll just explain some of the things here. Actually, maybe I'll start with example 0, which is not on the slides. So for this, if G is SL2, as we said, and so that N is A2 minus 1, mod plus minus 1, then you can take for A to be just polynomials, functions on A2, smash prod minus 1. So A is really defined more up to Morita equivalence, so this is possible representative. And then in the more general case, I just want to give you some partial information. So if E is subregular and important in SLN, meaning it has the Jordan block, two Jordan blocks of size 0 and n minus 1, then so I want to I'm telling you what are the irreducible A modules whose central character is that important, and what kind of complexes of coherent sheaves they correspond to. So the fiber here is known to be a chain of projective lines, and the sheaves are as written here, just O of minus 1 on each line shifted by 1, and then O of the union. So these are the same sheaves that appear and derive my K correspondence of correspondence 0. And then when G is SL2N and E has 2 equal Jordan blocks, I won't tell you what the what complex of coherent sheaves they correspond to, but I just want to tell you that what they index by. So they index by these arc diagrams on the cylinder, look like that, and then X from, so this is something that appears in Kovanov arc algebra cylinder. So you want to compute X from one such thing to the other, you should, I'll just maybe without writing, say that you have like one diagram, flip the other diagram like upside down, put them together, then you get a bunch of circles. You should take basically a vector space of dimension 2 to the number of the circles. In any case, so there's some. So this was worked out by my students, and then one paper was published recently. Okay, so now I want to talk about applications. Again, so I'm just listing the things here. So the first kind of applications is to descriptions of characters of irreducible representations of various things of interest in representation theory. And the motivating example was the representation of semi-simple algebras in positive characteristic. And we did it for large, indefinitely large characteristic. And okay, so maybe I list the settings and then I say how this application works. So what is really there that allows us to do this. Okay, so we first work with this algebras in positive characteristic. Another setting is quantum groups at the root of unity, which was just conjectures in our paper in 2013, but worked out by Tanisaki. So a series of papers over the years, culminating paper in 2021. And then there is application to affine the algebras at the critical level, which was only partly done. So part of it is an open problem, but it's worked out. And I just want to say that in all these cases, the category of representations with a given character, with a given central character. I mean, this is central character is the first in the representation. We'll look at representation theory. But the point is that it's identified with representations of the algebra A. Well, sitting at a certain point. So this is A tensor all functions on this important cone with C and sorry, kill the maximal ideal in centers of algebra in N, some element E in N. And so this is the manifestation of the principle that I mentioned, that in fact the K group of this AE is an irreduced can be given a structure of representation of H. So this is basically what Kazhdan constructed for back in 1987, but here we kind of recover some interesting representation theoretic stories as categorification. Any questions? Huh? Yes. For Springer part. So this is, it's kind of combining in the sense that the derived case. Derived category here in sheaves. One well, I call this map phi, then phi minus Sophia, and again thought of as the right side. Okay. Yeah. Other questions? No, fine spring fiber didn't appear yet. Just usual. I actually didn't hear. Did you ask about a fine spring fiber or usual? Yeah, yeah. Okay, so so there are other sorts of applications and applications in harmonic analysis, which are more. So here I maybe will not go into much detail. So I just mention that a recent application where we with Sasha Braverman, Michael Finkelberg, and David Kazhdan, where we construct local L factors for representations of p-adic group. But just what I want to emphasize here is again that there's something, it's also based on construction. So it's about constructing functions on the p-adic group, but taking trace of Frobenius of certain sheaves. But the key point here there in the story is that you kind of have a control over this sheaves in terms of the Langlands dual group. And the key ingredient is, again, the description of the T structure. And then there is a work in progress. But yeah, don't spend time on that. And I just want to mention one application that I was not involved in myself, so by Lee, Nadler, and Yoon, where they work towards geometric Langlands for elliptic curves. But I just want to mention the very concrete statement that they prove by heavily relying on this result, if I understand correctly, and its generalizations. So they take a group, a reductive group, take a variety of commuting pairs, and there is an old problem in commutative algebra to show that it's reduced. So they show that it is reduced, and they show that the ring of invariant function. So yeah, I don't know who is here, but yeah. Ask him if you're interested. Okay, so now I want to return to this, well, kind of be affine and the rhetorical question I asked. So first of all, I want to, yeah, so this noncommutative spring it appeared in the just by name, and I gave some examples, but I want to explain that this is really something completely controlled by this affine braid group. And so here is the characterization. This is the precise theorem. And so the affine braid group contains a positive braid monoid. And this, so it is defined, it has standard generators. It's I, where you consider this points on the plane, and then so the psi is when 2 points run like that. So this is just a group generating by them, but that contains the positive BF plus send generator. And the T structure on VB Coherent tilt, so which is from which A is recovered at the endomorphisms of the projective generator of its part, is characterized as unique T structure such that be affine plus X by right exact functors, and then normalization requirement that derive global section. So it's something completely controlled by this braid group. And there's a reformulation that I like, which in terms of a collection of T structures assigned to Okounkov, And so here we can consider this affine root configuration. It contains, if I consider the Kazhdan, real Kazhdan subgroup, and then it contains affine four-root hyperplanes. So this is for a type A2SL3, you get this picture. And so they partition the space into this alpha here. And so affine Bragg group is just the fundamental group of the complement of the in the complexification. If you quotient by double, closely related to this configuration of hyperplanes, and then you can rewrite this structure as collection of T structures assigned to Okounkov, and which in a way compatible with the affine action, and then this axiom, the positivity axiom, the top line becomes a sort of condition of monotonicity. You go one Okounkov is above the other, and the like D plus, yes, it's larger. And this structure is already, yeah, so here just mentioning it's related to Bridgeland stabilities, and this was established in this 2015 paper. And then, okay, you can advertise this perennial project so there's a theorem that the action of B affine on the K group coincides with monodromy of quantum equivariant connection. Maybe I should have mentioned this based on result of Cherednik, computing both sides, and then this can be generalized to clear varieties. But okay, so this is so maybe I want to finish with explaining a certain maybe something that can be seen as a stronger answer to the question that about topological nature of the B affine action. And so this is some paper in progress. Should appear somewhere. So there is a the natural place where fundamental groups act on triangulated categories is well, you have family of varieties, and you can assign a category to each variety in a way, in some locally constant way. Then you certainly get action of the fundamental group by monodromy. And there is this conjecture, but there's a theorem that closely related to that conjecture. So I'm basically providing you with a family of varieties over the base with this fundamental group. And namely, so remember that we said that the fundamental, that the affine Bragg group is a fundamental group of the set of regular semi-simple conjugacy classes in the dual group. So for GLN, we had this configuration of points on C star. So these are just eigenvalues of this invertible matrix. So for each such conjugacy class, we consider the intersection of this conjugate class with matrices that Gauss decomposition. So this is our family. But now I'm using this conjecture to motivate the theorem, which maybe I will explain in a little more detail on the board. So I have like 5 minutes for that. Yes, so so this is the almost finished paper. Basically, while we do not work with the Fukaya category, because it's not our home territory, we prove something unrelated, namely, what is written here is a kind of indication of the relation of a theorem. Is not fully stated, but I will probably state it more fully now with this conjecture. So the point is that this variety, it appears as a modular space of certain irregular connections on CP1, and so there's this framework of non-abelian Hodge theory. But to this, in that framework, so there's Betti space, and then there's the Ram space, and then there's Dolbeau space. And so our actual theorem is about Dolbeau space. And it has to do with the a category and Dolbeau can be described as the quotient. So the space LG mod I, defined flex space, already made its appearance. And so we consider the potential variety, and then we consider the Hamiltonian reduction of the group psi, where P minus is subgroup into G of a T inverse. So there was before we had that's congruent subgroup. So the kernel of the reduction 0. And psi is its generic character. But what is, so maybe it's not so clear from this description, but the actual space whose geometry is involved here is the affine Springer fiber, as anticipated. So this contains the Lagrange 4. And affine Springer fiber. So here S is in G, just you can think of it as diagonalizable matrix with distinct eigenvalues. T is our uniformizer. So T is coordinate on that function disk. And this is just the set of fixed points of this matrix. Right. So the maybe I should mention the example of SL2, where this is fine Springer fiber is just an infinite chain of projective lines. Before we on one of the slides we had a finite chain of projective lines. Got the infinite chain of projective lines, and so basically here we there is a description which is just involves sheaves, not microlocal sheaves, but the fastest way to say what we work with is microlocal sheaves on this thing, supported on this Lagrangian. So this is establishes a sort of relation of this category to geometry of this thing, and then it's also turns out to be the category of causal to representations of a small quantum group, thereby establishing this new geometric setting related to that representation. So maybe it's no, there were coherent sheaves. Here it's some sort of microlocal constructor. We are not coherent sheaves on this thing is not yet in the picture. So again, so this is affine, but sort of constructible. There it was coherent, affine dimension. So coherent here is more. Oh, we are not there yet. Well, just anyway, to connect it all together. Okay, maybe I'll stop here.
Are there questions?
In this last slide and what you were saying about identification with the quantum connection.
About between this and quantum connection.
Yes.
Yes, but not completely understood. So maybe I can. I'm no, okay. I yeah, okay. So that's what I was saying, that the monodromy is really transparent if you use the Delbour. Sorry, if you use the Betty thing in Fukaya, which we don't do. Yeah, but so again, so this, I think there are maybe results in the literature that microlocal sheaves on like this thing should be related to Fukaya. Huh? Okay. So, but modulo that. So I mean I mean there's even in the I mean assuming we can work with Betty picture, but I don't have a good way in general to extract this quantum connection from that, because so this is a question that maybe we discussed many years ago too, but I mean there's some I tried to. I mean, the issue is that the quantum connection is the equivariant quantum connection for dilations, and there is no good understanding, as far as I understand, how to recover it there. But even so there's Gauss-Manin connection, which is a sort of degeneration of that connection. And what I think is that this connection with this variation of port structures really captures a lot of information about the dual side. But that's maybe something I'd love to.
Does it connection make sense, right? And it is what you expect. Something like this?
Yes.
Something like this.
Yeah, had a related question. So in the field variety setting, what is discrete group action? How to construct it?
How it's constructed?
Yeah.
Well, we have a construction using this characteristic P, a quantization, which, yeah.
Can you say,
Well, I mean, here,
can you say how it's
well, in one word, I mean, we can discuss more, but like in here, there are this. So let's go back to this picture with Alkovs, right? So there was this picture with Alkovs. And so, well, I didn't talk about it today, but I'm sure you heard me talk about it at other places, that this braid action can also be constructed in this way, that you can sort of consider twisted differential operates with various parameters, and then if the parameter divided by p lies in the Alkov, you kind of. So you consider well, I said they have a collection of structures, a collection of non-commutative resolutions indexed by Alkovs, and you pick a quantization parameter which lies and divided by p falls into this Alkov, you get sort of functor to that models over that quantization, and somehow comparing these different things, like you get various functors and combining them.
Yeah, I memorized that.
Yes.
I have one more question.
Yes.
So here you consider coefficient is C, right? I mean, how
Yeah.
about the modular case? Can you say something about the modular?
modular case for the fine Hecke algebra?
Yeah, I mean for the particle characteristic.
Well, you see, it's not, I mean, I don't know, but I haven't thought really. But I mean, in terms of realizing H affine in the as K group, I think this works with Z coefficients. And then we had this representation. So yeah, like you're saying that, okay, I said that here, right, this is like K group of this is the representations of H affine coefficients. But I mean, if you're asking whether you can look at the root of unity and categorify the representative of a root of unity, that can be very interesting. That's not. Or your model. Anyway, I don't know, modular you said, but anyway, yeah, maybe the answer is I don't know.
Other questions? Okay, if that's not the case, I thank Roman again.